I'll start with a quick overview of virtual dynamics and its capabilities in a nutshell with a few slides and in a few minutes, and then I'll hand over the words to Pascal. What is virtual dynamics? It's an advanced simulation software for dynamic analysis of engine, transmission, driveline, electric motor in conventional, hybrid, electric or battery electric vehicles. So we create virtual prototypes of engine, transmission, and driveline in component level, subsystem level, or assembly level. Then we put these virtual prototypes in the virtual test bench and carry out virtual testing, or in other words, simulation in the mechanical dynamics domain. So that means for engine, as an example, we can model and simulate timing drive on its own, valve train on its own, crank train on its own, or we can assemble everything together and model and simulate the entire engine assembly in mechanical dynamics domain. It is not limited to engines. We can also do transmission, hybrid powertrain, or electric drive units or e-axles. That means electric powertrains in battery electric vehicles as well. So I say mechanical dynamics domain. So what we mean by mechanical dynamics? Virtual dynamics calculates forces, displacements, deformations, and their derivatives in time in component level, like valve spring, model and simulate on its own, or put this spring into a single valve train system with flexible components, or build an entire valve train system with flexible camshaft and flexible roller finger followers, or we can couple valve train to crank train by using a timing drive. And at any point we want, we can calculate forces, displacements, deformations, and their derivatives in time. So why do we need forces, displacements, and deformations, and their derivatives? If I try to list typical problems and challenges we can address using virtual dynamics is, so one of them, we can build a virtual test bench. So we can have our powertrain in a virtual test bench, and in that virtual test bench, we can have thousands of sensors. At any point we want, we can predict forces, displacements, and deformations, which is practically not possible in the physical test bench. We can assess the durability of components. For this particular example, what you see here is a crankshaft that we can assess the durability, but it is not limited to crankshaft. It can be any flexible component that we have in our powertrain model. It can be engine block, connecting rod, transmission casing, transmission shaft, or gears, or any other component that we can model as a flexible body. So today's subject is mainly friction, engine friction. So we can predict engine friction that you will see in the coming slides, how we do that. We can predict friction and reduce the friction. That will be an increase in mechanical efficiency, and it will eventually result in less CO2 emissions. We are also able to calculate surface vibrations by means of velocity or acceleration or displacement, so we can assess the NVH behavior of the powertrain. We are also able to calculate scuffing and wear in the interacting surfaces like bearing, shafts, piston, liner, ring and liner, and so on. We are able to predict lubricant oil consumption, blow-by, blow-back gas flows. We can also look at the entire driveline dynamics with the detailed excitations coming from engine and transmission. This slide summarizes the typical fields of application. So the core application area, of course, IC engines, like valve train, timing drive, crank train and bearings, piston group, connecting rod, including variable compression ratio connecting rod. Turbochargers is also another application area. It is not limited to engine, as I said at the beginning. We can also model and simulate transmission, test bench, vehicle driveline. AC compressor is just an example. We can basically model and simulate any mechanical system. We also address the e-mobility topic very well. We have a dedicated electric motor component that we can use this in EDUs, hybrid powertrains. We can also model and simulate range extender or belt starter generator systems. So that said, we can move to the main topic of today, friction optimization. And now I hand over the words to Pascal.
So, thank you very much for the introduction to our software environment. That takes off a lot of effort for me to present all this. And we will now start on the topic with friction optimization. And I'm going to show on how to simulate friction using virtual dynamics, how to calibrate the friction models using data from FEV database or the test bench. I'm going to show a lot about the friction approaches used for efficient and performant simulation. And I'm ending with a small success story about the optimization of a single camshaft friction. So basically, the motivation behind this friction simulation with virtual dynamics is to avoid the necessity of acquiring hardware to do some parameter analysis in terms of friction optimization. So here we are using the commercial software environment virtual dynamics to optimize friction for our subsystems. The precision of friction calculation can be adjusted dependent on the needs. So if you want to have a very detailed look into friction modeling, we can shoot at the problem with some EHD formulations, or we can use rather simplified approaches that cover the major impacts. So on the right side, you can see I brought a small example of such a friction simulation. You can see that there is a single camshaft with a front roller bearing, and the camshaft bearings are modeled as a hydrodynamics model with some asperity approach. And you can see that using this approach, it is possible to match the friction tendency on the test bench after calibration very well, and to be able to split the total friction into the sources. We have a very advanced piston analysis model as well, shown on the bottom, where it's also possible to review the breakdown onto very detailed components like the piston rings, the piston ring shape. Yeah, this major impact here, PLC, means piston liner contact, so basically the piston skirt and liner interaction. And here at the bottom, the pin bearing, of course, is referring to the crank pin bearing. So FEV uses several approaches on how to cope with the topic of friction. On the one side, we have the friction database with a lot of series production engines as well as FEV developments. There are over 1,000 measurements available for more than 600 engines, where we can get the system level frictions from. On the right side, we have the capabilities to review the losses from the hydraulic system of an engine application using 1D simulation. And the gap between these hydraulic losses and the system level analysis is filled with the component level friction simulation using virtual dynamics. So in order to allow an efficient workflow for the simulation, it makes sense to not couple all the subsystems together and having one huge simulation model with a lot of parameters that takes a lot of simulation time, and on the other side ends with a very complex matrix for doing design of experiments. So this is why our approach foresees to split all the subsystems of an engine to split the whole engine into subsystems. In order to do so, I have brought a small example on how we approach the friction analysis of a whole valve train system, including the timing drive. So in step 1, we are doing a full flexible analysis of the single valve train in order to derive some torques that can then be applied on the camshaft sprockets. We are doing a crank train analysis, also full flexible, and impose the resulting cyclic speed irregularity on the crank sprocket. Both information together allow us to simulate the timing system. From the timing system simulation, we are able to obtain the hub loads, which could then be imposed on the single camshaft. So this is our approach on how to reduce the parameter matrix and how to speed up simulation and calibration time. I will continue with the example of a single camshaft simulation. What you can basically see here is which friction approaches we are going to use for each element. So, as originally mentioned, for the camshaft bearings, we are using a simple 2D hydrodynamic bearing model, which is very efficient but gives us an accurate impression on the remaining lubrication film heights. And we add an asperity model because, especially on low engine speeds, it is usually the case that you see larger impacts of friction due to asperity on the camshafts. For the roller contact between the cam and the roller, we are using an Adams friction approach, which considers a friction coefficient that is varying over the sliding velocity. For the valve guide, we are saving efforts for valve secondary motion analysis, and instead we are doing an analytical Coulomb approach that estimates the side forces between the valve and the guide and calculates friction dependent on the side forces. For the hub bearing, we are using a roller bearing approach that is pretty much relying on the information from bearing suppliers who investigated the friction amount on empirical basis. Same counts for the roller bearing inside of the roller finger follower. And for the valve stem contact, we are also using the Adams approach with the varying friction coefficient over sliding velocity. Just to give you an impression of what these friction approaches look like, we are using and why they are so efficient in simulation performance. I'm just giving the example on how the camshaft bearing models are. So we are basically measuring the eccentricity between the shaft and the shell of a bearing, and we are comparing this with an asperity information which you can usually retrieve from a technical drawing of a component. If the eccentricity of the shaft inside the bearing in the 2D hydrodynamic bearing model gets so large that the shaft gets into contact with the asperity peaks, an additional torque is applied as a resistance to the shaft rotation. For the roller bearing friction, we are having a very simple approach based on the empirical formulations from the supplier catalogs. So for the roller bearings, you typically have easily obtainable parameters from the design or from the oil you want to use for your engine. Then we have two parameters which can be obtained by reviewing the roller bearing properties in the supplier catalog. The factor F0 and the factor F1 are both obtainable from the catalogs. The one is giving a factor for the rotational speed dependency of the roller bearing. The other one is a load dependent factor. Just to mention that we are not stopping here with these empirical formulations and the friction caused by simply the rollers. We are also able to consider the effect of a sealing in your bearing, like for the water pump or the oil pump in your auxiliary drive. So this sealing friction formulation can be obtained by the SKF catalog. By this formulation, the parameters are also obtainable from the catalog if you have a certain dimension and selected a certain sealing which fits your needs. Regarding the analytical approach on how to estimate friction between valve and valve guide, we have put up an analytical way to calculate the friction. On the top side, there is a sliding motion between the roller finger follower and the valve, and there is a sliding velocity causing some tilting torque onto the valve stem. Further, the contact has a certain eccentricity, and the normal force is acting on the valve stem end, imposing another contribution to the total valve torque. This torque is split over the lever arms between the guide top position, guide bottom position, and the valve stem tip into some side forces. These side forces are then multiplied with a friction coefficient, leading to a resistance to the valve motion. As a second part of this friction formulation, there is also a Couette flow model added to the valve resistance, simulating the impact of lubricant inside the valve guide. Coming more to the timing system friction. Between the chain and the chain guides, we have the opportunity to enter Strebeck maps that give back a friction coefficient dependent on the chain velocity and the chain contact force. These Strebeck maps, they can on the one side be calculated using EHD simulations in some kind of pre-processing, or they can be obtained by reviewing some EHD theory that considers also surface roughness, link contact geometry, lubricant properties, and material elasticity as impact factors on the friction coefficient map. In this way, it is possible to review the impact of changes of your chain link backside convexity radius, maybe also of the guide materials, and also of parameters like the surface roughness. Another larger benefit here is that Virtual Dynamics is capable of using real 3D models in order to model the contacts between the chain and the sprockets. So here you have a close picture of the engagement between a silent chain and a sprocket, which is, and the friction calculation is considering all the relevant forces and sliding motion to give a very accurate feedback about the occurring friction. If you want to avoid and save some time when iterating with several designs of silent chain tooth geometry or sprocket tooth geometry, it is not necessary that you always have to ask a designer for some chain design updates and sprocket design updates, exporting data and importing data back into the simulation model. You have also the opportunity to use the integrated parametric geometry model inside of Virtual Dynamics to do this kind of study and save the efforts for your designer. This comes with another advantage. You can split the causes of friction into different zones of your chain links and sprocket engagement. So you can review very detailed impacts of your chain optimization and the impact on friction. So just to give you a small impression on the one side of the quality which is obtainable after some calibration using these friction approaches, and also a small success story of the friction optimization of the camshaft, I have brought this slide. So here you can basically see that with a measurement performed on the FEV test bench for motor friction investigation, we are able to match the full trend after parameter calibration using our friction approaches. The same counts for the timing system, where it is also possible to model effects like the resonances and their impact on friction. So based on this excellent calibration, it is now possible to vary parameters, like in this small study, the valve lift curve, come up with a new valve spring, and with a new bearing size in order to lower the amount of asperity and in order to reduce damping losses in the high engine speed range. So here it is especially important to lower the asperity friction, because in actual driving cycles your engine is likely to operate on very low engine speeds. So such kind of study can help to lower the contribution of the valve train friction onto your total engine friction. Showing also that this work split, reviewing the subsystem friction and putting everything together back to the full engine, it's also working for the crank train. I have come up with a small slide from the crank train analysis. So here it's shown only a crankshaft without the piston group, which rotates inside of the main bearings. This model is considering the hydrodynamic 3D bearing approach, that is also considering the effect of reduced oil film heights due to bending and misalignment of your crankshaft inside of the bearings. It comes with the consideration of a torsional vibration damper and a single mass flywheel. These components can start flattering and increase the bending on your crankshaft at high engine speeds, and therefore it's also considered that the crankshaft is modeled as a flexible structure. So using this very simple simulation model, it is possible to match the relevant friction parameters so that you can achieve a very good correlation to the necessary measurement of friction. The piston group analysis is separated. For the piston group analysis, we are doing single cylinder analysis because each cylinder has a different bore distortion and therefore has a different contribution to the whole friction. If we add both approaches in the end, it is possible to put crankshaft friction and piston group friction all together and compare this with the measurement of the total crankshaft and piston group together. You can also see here that, considering this bore distortion, a very good correlation between the measurement and the simulation is possible. So, thank you all for listening. I want to briefly summarize our outcomes. So, Mustafa has presented virtual dynamics as our all-purpose tool for multi-body simulation, transmission investigation, engine investigation, as well as conventional and hybrid and electrified powertrain investigation. Here we have used our tool to optimize the engine friction on a component level. Our method includes the calibration of our multi-body simulations using measurements from FEV or some other measurement data available, and splitting those frictions into the shares on a single component level using physical friction modeling approaches. From there, parameters and parametric studies of components can be carried out to investigate the influence on the total engine friction and to optimize engines without the necessity of costly hardware.